Thank you all for being here. Very excited to be here with all of you in Denver, Colorado. Thank you for, so that we're going to watch this video later online. Today we're going to talk about low latency trading system in C++. So I'm David. I've been working in trading in the industry for about 10 years. Always at Optiva, market maker. Before that, I was working on relatively similar systems in a very different industry, in defense. And today we are going to talk about engineering low latency systems. I like to put the emphasis on engineering because it's not going to be a very theoretical talk. We're going to be looking at actual problems that we want to solve. And throughout this talk, we're going to look at some principles along the way. Some of them that I collected throughout my career that I found are important and I think that could help you, and also some profiling techniques. But before going into the technical details, let's backtrack a little bit by around 2,500 years where most things started, at least in the Western world, which is the antiquity. We start with the Roman Empire. And there are many things that are actually fascinating about the Roman Empire. But at least, two of them are, which is, it lasted for a very long period of time and it was already vast. It went from like the Hadrian Walls in modern UK to, modern Iran, which is Persia. And, historians in general do not agree on a lot of things about Romans. For example, the reason of their decline. But they all agree on one thing, which is the key to their success, is that they were very good at planning things. They had a really good infrastructure and organized. They were very disciplined. Now, what did the Romans plan? Well, a few things. Here I have some example. Urban food supply, military campaigns. They're really famous for their military achievements. Now, something a little bit more fun to talk about than military achievements is festivals. Here you have pictures of Circus Maximus, which you can still see the rest in Rome, in Italy. And it has an estimated capacity of 200,000, 300,000 people. So they weren't organizing small parties there. And if you wanna, if you're organizing such large events, you have an interest into planning things for your economy. So what the Romans actually figured out, and what they did is that they would actually go to, farmers, winemaker, etc. They needed some grains, some meat, all kind of things for these events. And they would ask them, a year from now, at what price would you be willing to sell, that grain? And by doing so, the Romans invented very much, early derivative trading. It was actually called Roman future contracts. And so what the Romans figured out is that the world had a certain uncertainty. And so when I was preparing this talk, I actually learned about this index called the World Uncertainty Index. Now what you can see on that, on that blue line, you mostly see relatively, let's say, negative events. Doesn't mean it's all bad, but it's mostly that us humans are psychological creatures and we attach more weight to potential loss than potential gains. I think that makes sense. Usually if you cannot sleep at night, it's mostly because you can actually lose something, more actually if you can make some profit, right? You can relate to that. And so back to the Romans, they indeed found a solution to, reducing the world uncertainty by doing derivative trading. One thing that they didn't actually truly solve is usually when things are quite uncertain, you have also potentially a problem of liquidity. And I think it makes sense to think that if there is a certain economic turmoil and there is a lot of uncertainty in the world at the same time, people would be less likely to actually agree on a price a year or even 2 years from now. Because, who knows what can happen. Now, going into, the modern world, that's why we've got market makers. And I like to ground that talk into the reality. And so, at least my reality, I've been working for 10 years for a market maker, so that's why we've got that. There are many different actors, of course, on the financial markets, and today we're going to talk about low latency, and many of these different actors have different requirements in low latency. We'll come to that in a bit. We say that market making is a loser's game. And so what we mean by that is that effectively, you need to be consistently good at pretty much everything, right? It's not about this one silver bullet that's going to allow you, to beat the market. You need to be constantly good at everything. And so effectively, what market makers, how it works is that you make some small profit. And the small profits are from, well, back to the Romans, you agree on a price a year from now. And, most of the time there is actually, you actually gotta pay for this small, optionality. It can't be free because you have some risk, prices might go up and down. And you want to avoid big losses. Now, why would you actually lose a lot of money? You're providing prices at any point of time of, 100,000s of instruments. And there is a news. News come out all the time, but there can be a big news that comes out. And, what would happen if you just leave all your price unchanged? Well, you would have actually, stale prices, and you would do actually a lot of bad trades. So that's what we mean by like a loser's game, consistently good at everything. Now, elaborating a little bit more about, why do we need low latency programming here, breaking down this into two categories. I think the first one is relatively well known. I think it's the most intuitive one, which is we wanna, we have a need for like reacting fast to uncertain events. That news that I just mentioned, that news that comes out, we need to react. We need to effectively update our price, or maybe just cancel our orders. The second one is a little bit maybe less straightforward, which I'm going to explain on the next slide, which is you also need to be smart. Now, like being smart is a relatively vague concept. So you need good models and so on and so forth, but you also need to be accurate. And again, accuracy is inherently related to latency. Again, for the same idea of like you've got an information flow into your system, and you want to, you want actually to have like accurate prices. You want to ingest this information. So on this slide here, you can see what I would call a relatively standard, modern trading system. And the reason I put that slide here is like one of the questions that I get most of the time when I go to conference or like in general is, hey, we've got FPGAs. They are really fast, so why do we still care about software? Why do we still care about low latency, C++ in that case? And so there are two answers to that question. So on that graph, you see the exchanges on the right. Price are disseminated into the system, so they flow into the system. And so indeed, you've got that blazing fast FPGA here. I'm going to say a bit more about it in a bit. Why do we still need, to send orders even with software? It's just what I would say is cost benefit. An FPGA is expensive, not the card itself, but just the engineering time, or just like operationally, it's something more complicated to manage than software. Software is more flexible, so it's always going to be there. It's kind of hand to hand. It's just engineering your system properly and finding the right solution for the right problem. So that's on the right. Now there is something a little bit deeper on why we need low latency software, which is, you see the yellow boxes on the left, the strategies. What the strategies are doing is that they send so-called, we call them rules to the FPGA. The idea is that for the FPGA to be blazing fast, it has to be really simple. Now, I don't mean that it's a simple thing to engineer. It's actually quite complicated. But functionally speaking, it's very simple. It sees bits, compare bits, and send bits. You could actually make it more complicated, but it's just a trade-off. Then it would be slower. And so the strategy sends this rule. So what is the rule? Very simple. If price greater than 10, update my price or cancel my order. And so now if you think about it, the strategies themselves, they have already low latency requirement. Because if, for example, we would only update these rules every minute, or even every second, with all the information that flows on the world, on markets, we would have, again, stale prices, stale information. Lots of people would be really happy to trade against you because you do mostly, you do trade on like old information. Now let's get into, some more technical content. One of the first data structure, I was thinking when preparing this talk on like, what would be something nice to talk about, and like a data structure that is actually very interesting is an order book. Now we're going to define it in a bit, but why it's interesting is because no matter, like the trading system that you're working on could be algorithmic, manual, pretty much anything, you always have this core component. You always ingest price from the exchange and you want to know what they are. So let's quickly define what it is. On the left, you see the bids. That are the prices at which people are willing to buy. So you see $92 is what we call our best bid. Why is this interesting? Is because if you want to sell, this is actually the price that you're going to sell at. There is no reason for you to sell at $90 or $85 here. There is also, you see 50, the 50 stocks. This is actually the total amount that people are actually willing to buy at this level. So there might be one or multiple investor ready to buy at this price. Similarly, you've got asks. Same story there. Some people are willing to sell. This is, you've got the best ask, $95. That's the best price at which you can buy. Why is this interesting in today's talk that is mostly going to be about low latency programming? Is because you actually do have a lot of low latency constraint and requirements in this data structure. At the very least two, these are the two main ones. If you do algorithmic trading, again, back to what we said before, you want to be as accurate and fast as you can. So you ingest these prices. And so you want a really fast data structure. This is your first one, effectively. You want it to be fast. And the second one is a little bit different. It's more like, I would say, a system constraint, is that you have a network card. The network card, as pretty much any physical device, has a finite number of buffers. And if your application is not fast enough reading from these buffers, you're just going to, the network card is just going to drop. You're going to miss some of them, which will cause an outage. Now, going through some properties of this order book, we have two sequences that are ordered. You could argue, we could have them unordered, but I try to put some emphasis on why it's important that effectively these prices stay ordered. So that's what we need. Concept of price level, we talked about it, you have a price, you have a volume. Each order that is going to come into this order book has an ID, UN64. And an important property is that a typical stock order book, today we're going to look at stocks, has around 1,000 levels per side. Looking at our API, it's relatively straightforward. Now, every exchange, there are many exchanges around the world. They all offer slightly different messages, but in general, we've got an API that looks like this. This is not too crazy. It's relatively standard. And so we've got like an add order operation. There's a new order comes in at the price volume, modify and delete. So let's go through some example. We want to buy at $92 for like 25 stocks. So we're going to join that level. So we go from 50 to 75. Then we add an order on a level that doesn't exist, $110. So it's inserted. We modify our first order. We're only interested to buy 15 stocks now, not 25 anymore, so it's a reduction of 10. And then we can also delete. An initial observation that we have is, looking at this API, especially the delete operation, just as an example, but modify as well, is that no matter what data structure we're going to use for this order book, we need a hash map. Right? We need a hash map around it. For the reason that, yeah, again, the delete, we only have the ID, so we need to retrieve the price volume sign. Now, today we are not going to talk about hash map much. Main reason I didn't really want to talk about hash map is that there are many talks about it. It's a very, very well documented engineering problem. So I'm not gonna talk about that. The most natural data structure that you can use for this order book is StudMap. First, we're gonna go through a bit of code, and then I will explain why this is the most obvious natural implementation that you can do for this data structure. Right, you've got two StudMap, one for your bids, one for the ask, because they are ordered differently. So the implementation is relatively straightforward. In the add order, we try to emplace. If the emplace succeeds, awesome. That means that the level didn't exist, we inserted it, nothing else to do. Otherwise, we update it, we add our volume. The delete is also quite straightforward. The main thing to see here is that we take as a parameter the iterator. And you see that the add order effectively returns the iterator. The idea here is that for the operations we are doing, StudMap has a great advantage that the iterators stay valid, at least for the operations we are doing. And so that's awesome, because we can store the iterator in the hash map. We're already doing the hash map lookup, so might as well use that. And so this is what I meant with this is the most obvious natural data structure for this problem, because complexity-wise, it's actually really good. I actually think that this is the best complexity that you can get for this problem. If you find something better, you can email me. But it's pretty good. It's the add is log n, otherwise amortized constant. Now this is what we get. So we're going to look at today various measurements. But here, when we look at a data structure like this, I find it important to look at the entire latency distribution. For the reason, if you would just be looking at a few percentile or median average min max, you'd be missing some information. This latency distribution it's not a micro benchmark, it's also not from production. When I was preparing this talk, I gathered it's a full week of market data on dozens of stocks, big tech stocks, like Microsoft, Nvidia, Tesla, and so on. And so, yeah, that's it, not production, but also not like a micro benchmark, somewhere in between. And so this is what we've got here. We see a distribution. Not too surprising, we see two peaks, one on the very left, which is the case for the modified delete when we only do a hash map lookup, and then a bit more to the right when we go through our binary tree. Now, effectively, this first distribution, I usually call it's a bit of a lie. And so this is the true, what I call the true story, the real distribution that for this data structure. And so what I did here is between the order book operation, I just added some memory allocations. Not really to really do much with them, but just to randomize the heap. And this is mostly because the most modern malloc implementation, they have this thing that is at the same time great and also not so great when you measure, that when you call malloc several times, you get actually contiguous block of memory. And so, yeah, that's great, but it's also not so great if you actually want to know the performance of this data structure, how it's going to behave in production. And so very much here, we are messing a little bit. We're kind of we are checking and measuring how, the cache locality of StudMap. And we know that it's going to be relatively poor, right? It's a node container. So in production, it's very rare that there is I've looked at quite some trading system, and it's very rare that there are zero dynamic memory allocation. We all know they aren't great, but there are always some around. And so this is replicating this pattern. And so I said that we will go through some principle along the way. So this is our first principle. Most of the time, you do not want node containers, right? So the entire family stud map set, unordered map, unordered set, and stud list, of course, but this one is really obvious. You put that on the side. In general, you don't touch them. That reminds me actually a talk of Sean Parent at CppCon. It was around like 10 years ago, maybe 15 years ago. He was saying roughly the same thing. At Adobe, in Photoshop, 90% of the time, they only use vector. Not because it's simple, not because they don't need other data structure, but just because there is a performance aspect to it. And of course, closed hash map, right? Hash map backed by arrays of vector. And so here, like you see this, on the picture, you see a developer that is this land of despair trying to fight this kind of ghost of like the node containers, and it's going to be really hard because it's everywhere or nowhere, right? So that's going to be a tough fight. This kind of remind you maybe some stories. I witnessed a few of these stories several times in my career, where there is a team of engineers that have as a mission, they go on a crusade to improve the performance or make fast an application that hasn't been designed to be fast. And therefore using this kind of containers and data structure all over the place. Usually, when this happens, you look at them from far and you say, good luck, because it's going to be really hard. Most of the time, you actually need to go back all the way to the drawing board, develop it from scratch, which is quite bad, actually. You should never do that. So moving on, what are we doing? Yeah, we use stud vector, lower bound. It's great. It's like cache locality is as good as you can get. cplusplus 23 brings the support, by the way, of stud flat map. I don't think the support is there, at least not in the version of GCC or Clang that I'm using. So this is what we use today. The complexity is really different than what we got before. We now have, a logarithmic complexity for add order, but if we need to insert a level, vector inserts is no secret, it's linear. And then we cannot store the iterator in our hash map anymore, right? That doesn't work because we are modifying our structure and the iterators are not valid. So complexity is much worse. Implementation-wise, relatively straightforward. We do lower bound. If our level exists, we adjust it, otherwise we insert it. And so this is what we get. See in green, we've got this new latency distribution for the vector. And so I would say that this latency distribution is fine. Does anyone have an idea or want to say, why it is just fine and not so good? Yes, there is a really big fat tail, which is absolutely not what we want on such system. We want something really narrow. And so where does this tail come from? To answer that question, we need to look at the data. Because here we are actually not, this data structure is actually quite specific here. So looking at data, so what does this graph actually shows? So I picked one of the stocks that I had, NVIDIA. And so we look at the distribution of the updated levels. So what that means is, so you remember before we were talking about best price or top price, these are index 0. And then when we go deeper into the book, 1, 2, 3, and so on and so forth. And so here, this graph is, by the way, in log scale. There are two ways of saying that. Scientific way is the updates are exponentially distributed over price. The simplest way of saying it is the action is happening on the top of your book, right? It makes sense. You have best prices where people want to buy and sell. So it's constantly disappearing or improving and so on and so forth. Now, what that means for data structure. Our vector effectively, we're just humans. The most intuitive ordering for this vector was to have our best price at the beginning, index 0. Right, so this $92 best bid was in index 0. So we just follow our intuition there. The problem is that with what we just saw on the previous slide, we're going to shift continuously our levels in memory all the time. Shift our elements in the vector. And so, good news, the solution is relatively simple. We can just reverse our vector. It's a relatively small code change, bit less intuitive, but now we are minimizing the amount of copies. Or moves, it's the same, like with these types that we've got. And so we have a much nicer latency distribution here. That tail is just completely gone. So that's awesome. So that brings us to our second principle, which is kind of like, a different way of saying this old quote, which is like a problem well stated, half solved. So yeah, you need to understand your problem. This is very much an engineering problem. If you just go head down into the data structure, not looking at, what's around it, very much like the business domain, you will be missing out. And the third principle is also really important. This is a very specific problem that we're going to solve here. And we need to leverage these properties, these very specific properties, in order to get performance. Otherwise, it's going to be very hard, right? We can't really get anything much faster if we don't leverage some of these underlying properties. And of course, to leverage them, we need to find them. And so here, in the picture you see on the left, we've got this very down-to-earth engineer, pragmatic engineer. And then on the right, more kind of like in the sky of the ideas thing. And we need both, but very much we are now in this talk on the left side. Actually not just in this talk, but when solving a specific problem. Now, how do we go faster from there? We're using perf. So here I'm just gonna show a little bit how I'm usually doing things. This is not gonna be extremely accurate, so it's not gonna work, or should I say, it's not gonna work for a micro benchmark, or if your benchmark is really short, this is definitely not gonna work. But in my case, in general, my benchmark, and not micro benchmark, they take seconds or minutes. So effectively just forking, running perf is awesome. The idea here is just that you don't want to measure anything about the initialization phase, because there you have actually a lot of stuff going on, and you don't want to measure that. It's not interesting. And the first measurement that you want to do, and this is actually really important because I see this mistake actually being done over and over. In general engineers, all of us are getting quite excited when you get to that stage, and so we start measuring everything and nothing. We just start, I'm going to measure the number of cache miss for like the level 1 data cache. Awesome. Why is that? Yeah, intuition. But in general, intuition is wrong. So here we need to be a bit, thorough, disciplined, like the Romans were. We need to be a bit scientific. And so you might recognize these different, 4 categories. I didn't come up with them. They are from the Intel TMAM, which is a top-down microarchitecture analysis method. And why these categories are really nice is because there is very little overlap between them, and you're also not missing anything. Right? So these 4 categories, retiring, bad speculation, front-end bound, back-end bound, you're not missing anything on what your CPU is doing. Now elaborate a little bit on what they mean. In the best case, every single of your instruction per cycle is going to be retired. So you have 100% there. Effectively, this never happens. You always have bottlenecks. But theoretically, on a theoretical workload, of course, depending on your CPU microarchitecture, I can only talk about x86, you've got a maximum, again, dependent on CPU, let's say 7 instructions per cycle. And so this IPC of 7 would mean that your 7 instructions per cycle will be all retired. And if not, then they would be, not executed because of bad speculation. Not going to go into details there. It could actually be an entire talk. But the main idea is there is usually it's caused by branch misprediction or front-end bound, usually around decoding instruction or back-end bound around memory. So that are the results that we've got for the code that we have, the one that we looked at with our stud vector. And so if you've never seen, if you didn't really measure or looked at these categories before, this is going to be maybe a little bit hard to get a grasp on if this is actually good or bad. My best advice would be start measuring, If you care about performance, you gotta measure. So start measuring pretty much anything. Your workload, some things that are more HPC, low latency, using data. And so very quickly you will have a good gut feeling of what these numbers should be. And so here I can tell you that the 25% of bad speculation is very high. So let's, dive into why is that. Perf record is awesome. It's a sampling profiler, so very different than stat. And it's going to give us a really quick, answer to that question. So what we see here, so what is this assembly code? This assembly code is still the same. It's our add order, delete order. If you remember, this code is really short. It's very much just lower bound, stood lower bound. And so what we see here, what's nice with this output is that we very quickly spot that 30%, more than 30% of our CPU time is spent on 2 conditional jump. And these 2 conditional jump are, in stood lower bound, it's a binary search. Although the CPU predictor is really good, it is still gonna struggle with the updates that we have. Right? We cannot yet predict the markets with our CPU predictor. That would be awesome. So that's our problem. So how do we fix it? How do we solve it? Well, we do branchless binary search. Right? If we just remove the branch. Now, there is something really important about branchless binary search. So we shouldn't get too excited too early, because the fundamental difference between this algorithm and lower bound, the traditional binary search, is that there is no early exit here anymore. So we're going to go through the entire collection no matter what, touching more memory. Still, it is going to be, we got a nice speed up here. We also see that we have 2 peaks in our distribution again. Can speculate that it's due to this effect that the branchless binary search is touching more memory. A lot of it is going to be really warm, and some of it less warm. Now, if you want to go a little bit deeper here, so just in the last tool, effectively not the last one, but another tool that you can use is that you can programmatically access hardware counters to be even more accurate. And so that's quite simple. You can actually just put it around your code, measure these counters, and so validate what your branchless binary search is doing. So you cut down the branch misses by 2, awesome. IPC going from 1.4 to 1.6, it's decent. You're never going to get the 2 times on your IPC. That would be huge. So it's a decent optimization. And then you can also see that indeed we are executing more instructions because there is no early exit anymore. So now the question is again, how do we go faster from there? Well, at this point, we need to take a step back and think about the operations we're doing. This is what binary search is doing. It's, we start our first pivot in the middle of the collection, we go left, right, and so on and so forth. The heat map here, well, effectively, it doesn't really represent the heat map for this benchmark. This is assuming a more, uniformly distributed updates. But still, it gives us an idea about, how warm or cold will be the element in our collection. At this point, you might think that, you might want to use, for example, an 8-singer array, because it's nice for cache locality, and also the access of the elements will be better for the prefetcher. Now, downside is of the 8-singer array is it's actually, there is a cost to build it. Also, the ordering would be different. So that actually doesn't really suit our needs. And from there on, effectively, when I prepared this talk, I already did my work of, I think, almost archaeologist or historian, right? Going through like all the possible order book that I could find. Adoptiver, also online. I think I measured like 30 different implementations, more or less complicated. And so we can go really complicated. I've seen really things that I was like, wow, this should be really fast. But usually it was actually not so much. And if we really think about the hardware, and how it works, the best implementation we can actually find, and the fastest, is linear search. It's blazing fast. It's very, distribution is really narrow, it's nice, there is no tail. And so at this point, you might be actually disappointed. And you should not. You should really actually embrace the simplicity of this solution and how fast it is. So this is our fourth principle, which is, this is when you know that you've done your job well as an engineer, when it's fast and it's extremely simple as well. At this point, actually, you can stop. It's awesome. And we also have a fifth principle here, mechanical sympathy. So what I mean here is you want algorithms that are in harmony with your hardware, which is what linear search is doing perfectly. Right? So it's great for, of course, your cache locality. It's great for the prefetcher, the way you access memory. It checks all the boxes, branches as well. Now, there are certain things along the way that I didn't mention, but are also important. They are harder to measure, mostly because they are around instruction cache. You can definitely measure them, but it's always going to be on your entire workload. Right? You need your entire application there. You need all the instruction executed, so you can't really, you can definitely measure some effects in benchmark, but it's going to be harder to reason about. And so one of them is, likely or unlikely, your compiler cannot know about your data, right? cannot take a guess. Effectively, without this keyword here on that branch, both GCC and Clang decide to move this add instruction at the very end of your function, which is, it's just, it's a reasonable approach. But what you want is actually to keep this add instruction very warm and packed actually with the instructions, because that branch is actually taken more often than the others. A second one is, I felt important to include it as a proxy on the, I guess, another point, which is there are actually a lot of talks and a lot of things online. People really like inlining things. And so there is a lot to be said about inlining and performance. And it's true. But there is also a lot to be said about not inlining things and how that affects your performance, the performance of your instruction cache in that case. And so you might have seen this expect on some of the previous slides. It's just an assert that you have in release build, right? So when you hit that assert, condition is false, you just die, just go down. And so effectively what you want there is you want to keep that code really far from actually the code that's supposed to be warm. And so that's one way of doing it, right? You really want that code far into a cold section of your binary and also not inlined. And so this is how the assembly looks like, and that's great. You have it really far there, and it's not messing with your instruction cache. Last point, also something that I actually have seen, I do see quite often. We did use lambdas on functors, and they are awesome, because the compiler knows the type, and so it can actually really go far into the optimization. If you were, in our previous example, if you were to use a stud function here, for some reason, if you were to pass it in your constructor, or just, I don't know, sometime matter of style, people comment, this lambda could be refactored. The consequence would actually be huge for the performance of this data structure, right? Because you lose, you lose type information. The stud function is using type eraser. And so the code generated would be, very different. I actually tried to put the assembly on the slide. It wouldn't fit, but the performance would be terrible with stud function. So now that we optimize this data structure, now that we've got this order book, nice, and it's simple and fast, the next thing we want to do is to send it around. So we're going to talk a little bit about networking and concurrency. The networking part will be relatively short because we're still at CppCon. But I still want to say a word about it. The general pattern is going to be to bypass kernel for your low latency connections. Could be receiving or sending. And once you're on a server, once you're on your box locally, you would just use shared memory to fan out this information to all the different processes that you have. And so here, again in this talk, not that I want to do any advertisement, but I'm only talking about technology that I'm using. SolarFlare, I think, is a relatively well-known industry standard for low latency NIC. And in general, it could be SolarFlare or other network cards that always come with like tools, and tools or library, should I call them. You usually have like, it's called open unload in that case. It's just a wrapper on your binary using LD preload that is going to hook your BSD sockets. And that's awesome because you can do user space networking without changing any of your code. If you wanna go even lower in terms of latency, and if you want actually a TCP stack, which is actually quite nice to have, you can use TCP direct. And if you really want to squeeze the last nanoseconds on your operation, on your networking operation, you would use a layer 2 API. It's called EFVI, or the equivalent would be DPDK from Intel. And so that's as low as you can get. You need to do all the buffer management yourself. But it's the fastest. So this is sub-measurements. I didn't make the measurements. That are actually from AMD. Again, not to focus on the AMD part that are the same with like most low latency NICs, but the idea here is to see the difference between the kernel and then onload and then EFVI. So this is for a UDP packet, and you see that you're on 3 mics for like your minimal size of UDP packet, and then lowest latency you can get it on 700 nanoseconds. That's where you are when using a layer 2 API. Which brings us to our 6th principle, which is kind of similar to the principle 4 about simplicity. It's like the efficiency, if you want to be fast and efficient, you should be mindful of what you're using. And so here you see an engineer, you're looking at this beautiful, big machinery that's on the left, which is the Linux kernel. I'm not saying that in a bad way. It's actually a beautiful machinery. It's awesome. But you should only use it, if you actually really need it. And in our case here, it's not a perfect fit for our needs, so you want to bypass it. Connecting the dots, so back to our trading system. We've got, again, exchange sending prices. Now we have this purple box on the left where we have our fast order book. We bypass the kernel, and then we want to disseminate this information into all the process on that box. We've got 50 strategy, let's say, and they all want the same order book. And so we will put it in shared memory, in queues. And on the right, you see, similarly, if you want to send orders, same story, kernel bypass, reading from the queues. Now let's talk a little bit about shared memory. When I was also preparing the talk, I was actually I asked on Reddit what people were interested, to hear. And shared memory actually came up a few times. Realized that, it's an industry standard. We use shared memory a lot, but it's not always very clear on like how or even why we're using it. So I wanted to say a word about that. The reason is, it's principle 6 again. If you're locally on a server, you just don't need sockets. So why would you use them? It's not because they are slow. It's just that you don't really need that. Effectively, if you would do user space networking on the host, that would be kind of weird. So you just want to use memory. It's awesome. It's as fast as it can get. You don't have the kernel involved, only when you map it. And I think the reason that shared memory is also quite popular and used is because you very much need it when you do multi-process. Right? If your architecture isn't really multi-threaded, right, you can just share data structure directly. But there is also an upside of doing multi-process, mostly for operational reasons. For not having something too monolithic, that if one strategy goes down, everything goes down, right? Kind of separation of concerns. What works well in memory? Contiguous arrays, awesome. That's actually what we want to use. That's also what's fast. And concurrency here can be, a little bit tricky. So in general, my advice would be, for one shared memory file, keep it to like one writer, one producer. In practice, how it works is very much, using the C API, and then we have a header that looks like this one. This is very much needed. You need to describe a little bit your protocol. So we've got here protocol name, magic number. This is very much needed because if you have 50 different protocols, you gotta be a little bit careful if at some point you open the wrong shared memory file. You might interpret the bytes the wrong way. And then you have minor, major version. Also very much needed. It's always really easy to engineer a protocol day one. It's much harder to have that protocol for years in production. And then you still need to make updates to that system. So you gotta version that protocol. And then in our case, we're interested to send still, this order book, so shared memory. So we have queues, and so we gotta describe these queues, how big are they? And from there on, once you have this header, you can, do a little bit of pointer arithmetic, and you have the full view of your shared memory. So there is a bit of low-level thing, but you can hide that around nice layers of abstraction, in C++. Now, concurrent queues. The one we are going to look at today is going to be bounded. So it's simple and fast. We don't want to do any resizing. It's not going to block. This is really important. Again, thinking of our trading system, we have 50 strategies there. If one strategy is too slow or has a bug, we do not want to affect the writer, because that would affect then all the strategies again, which would be problematic. We've got many consumers. We want to support message, variable length message. Reason here is it's nice to support message that are actually we don't want to just send pointers around, for the reason that if you have an architecture with multiple processes, like I described earlier, you actually want to send also data. Also, copying data is fast. Memcopy is fast. Sending pointers around can lead to other problems. Needs to do dynamic memory allocation, can lead to heap fragmentation, send pointers between different threads. We want to dispatch this information, so it's very much a fan out, so all the consumers get the same data. It's not a load balancer. And we support pods. So earlier this week, there was actually another talk about concurrent queues. So at the end of this week, you're all going to be expert in concurrent queues. The good news is this is actually a very different one than the one presented earlier this week. Right? So that's good. Principle 7. You have a lot of different things that you can choose from. And you gotta use the right tool for the right task. Right? Just presented a few different things, few different queues, and you need to pick the right one. Now, this is the queue we're going to look at for the next five minutes or so. We've got two counters, write counter and read counter. These two counters are both modified by the producer. Right? The producer has no idea if there is a consumer or not. They can be 0, they can be 50. Producer doesn't know. The consumer all read these counters. They don't touch them. They don't modify them. These counters have the same value. They point to the same element when there is no write operation. When a write operation is happening, the write counter is first advanced. So you advance the write counter, then you copy your data, and then you advance your read counter. Right? So they have the same point, the same element, advance, copy, and advance the other one. So very much the entire queue header is just these two atomics. Each of them have their own cache line. That's very much needed to avoid false sharing. And there are uint64. They grow from 0 to the infinite, so it's very much the number of bytes that we write to this queue. And our API is relatively straightforward. Yeah, as I said, we write bytes, we read bytes. The read might actually return 0. And so in the API for the reader, we have to pass, the buffer where we want to copy our data. Now this is simplified code, but not too far from the entire code. The only thing that's not there is the case to actually wrap around the queue. I think it's quite simple, and so it didn't really fit on that slide. So what you do here for the write operation, as I said, you calculate the size of your payloads. That's going to be, so we do variable length message, so we encode the size. So in that case, 4 bytes plus your buffer. You advance the write counter, copy your data, you advance your read counter. The reader is a little bit more complicated, but still relatively simple. So local counter here is just a local, it's a variable of our class. It's not on shell memory. We first check if there is anything to read, then we read the size. But before using that size, it's really important to check for our write counter, because there could have been an overflow. So we check for the write counter. Then we can use the size and copy our data. And then we need to check the write counter again. Now, what's important to note here is that although this algorithm is correct, from a language point of view, we've got a problem here. There is a data race, right? I mean, this stud_mem_copy, we are copying data while there is actually concurrent. So we have concurrent access on non-atomic variables there. And by the way, there is actually something that I forgot to mention, which is also important, is that the reason we do the stud_mem_copy on the size and not just using the equal operator is to avoid any strict aliasing or alignment issue, right? So you actually have to use stud_mem_copy. This is actually really important. So here we've got a data race. What to do about it? Yeah. In our case, as I said, the algorithm is correct. When we detect the data race, effectively we go down, we die. So I don't find it too problematic, but still, from a language perspective, it's not, we've got a data race here. A solution is in this proposal, bytewise atomic memcopy. You can actually implement it already now with the recent atomic ref, but you're going to pay for this latency, right? It only supports, 1 byte at a time. So you're going to pay actually a lot of performance for this. And you actually have the same problem with seclocks. Actually gave a talk at meeting CPP 2 years ago where I was using seclocks, and yes, seclocks are also a real problem. You actually cannot implement them. Could be in C or C++, in a very, correct way from a language perspective. Performance measurements. We're using an AMD Zen 4 architecture. It's tuned for low latency, core isolated. Its message is 73 bytes. Why 73 bytes? It's not too long, not too short. So I felt it was a nice number. And we compare it against 2 libraries, Disruptor, because it's, like the most famous ring buffer out there. And then Iron, which is a relatively well-known IPC library used in trading and other industry as well. Iron, by the way, is kind of baked into some more Java stuff around. So that actually I didn't use. I just picked the 2 C++ header file from the repo Otherwise, you need to instantiate some Java server to use some queues. Not sure if that shouldn't influence anything now. Oh yeah, and another queue, we're looking at this queue that I just mentioned, which is actually very different design. It doesn't have a header. It's using seclocks. I'm not gonna talk about this one today. You can just watch the talk online. It's a very different design. And so our baseline for this queue that we're looking at today is, I would say it's good, but it's not outstanding. So we're going to look at a few things on how to make it fast. And so the idea here is that very much, we've got these two atomics, and in order to make this fast, it's all about going to be the contention and the operation we are doing around these atomics. And by far, the biggest optimization you can do is to not touch the write counter on every message. So what we were doing is, we were effectively on every single message, we had this, moving the write counter, copying, moving the read counter. What you can do is, you can just say, well, I'm going to reserve 100 kilobytes. I'm going to move the write counter by 100 kilobytes in my queue. It will mean that readers will have 100 kilobytes less of data available to read, but it shouldn't be too much of a problem if you have 8 megabytes. You can choose another number. The idea is that if you have a 100 bytes message and you reserve 100 kilobytes, it means that you're only touching this atomic one every 1,000 message, which is huge. And so that's going to be really big because the readers, right? The readers are reading this write counter all the time. A much more obvious optimization, I still wanted to mention it for a reason that usually we like to align things on a cache line size. Effectively, there is no need to align things on the cache line size here, on x86, effectively the best alignment you have for your data is 8 bytes. You actually do not want to align that on a cache line because it affects actually the locality of your element, and there is not really a reason to align it on a cache line. Last optimization is also quite straightforward. When you read the read counter, if from this previous read operation, you read that there is 1 megabyte of data to be read. If you only read a kilobyte, you don't need to touch it. You don't need to read it again. These three things together effectively brings a really decent performance. So we're in green here. And so it's really good. Right? So compared to iron disruptor, compared to this seclock queue, so this seclock queue is interesting. It's actually faster in some case, slower in some other case. Effectively, the seclock queue is faster between, I think, 4 to 10 consumers. But in general, we've got something, again, quite simple and fast here. So back to our principle 4, and here I don't mean that we should all get out of, I don't want people to give the impression to people that, what I'm saying is that we should all now develop our own queues. Because still, concurrency is hard, but what I mean here is that when I was looking and doing a lot of benchmarks and looking at queues, I still often get a feeling that there is a lot of complexity that is not needed, right? Not trying to rant here or anything, but why would I need 100,000 lines of code with some really complicated system and framework while I actually just want a queue and shell memory that should be, 100, maybe 500 lines of code max. Effectively, this one is 150. If we want to go further, often what I see in APIs is that it's easy to get it wrong. So why is this API wrong, or why is it a bit disappointing here? Is that we need to pass to the queue a buffer that we're going to write to it. And what's a bit sad about this API is that it forces the application to serialize into this buffer, and then we're going to copy this buffer into the queue. Well, effectively, what you want to do is you want to be able to serialize directly into the queue. This actually can give you, depending on your serialization, of course, plenty of different serialization libraries out there. But depending on the way you serialize, this can give you easily a two times speed up, just with a simple API change and just opening the way that you write to that queue. And then you can go even further. I'm not going to elaborate here too much. They're just ideas. They're effectively things that we are doing, and there is actually more. Bulk writing. Yeah, bulk writing is really big here, because again, you can avoid touching even more your counters. And then you can have a queue that is more NUMA aware. If you have like consumer and producer that are, if your consumers are effectively on different NUMA nodes, could be different between the consumers. Not between consumers. I mean, different than actually the NUMA node of your producer. There is also something nice you can do there by duplicating, for example, the header with these two atomics. So now we looked at some data structure, looked at some concurrency. We used perf, we looked at hardware counters. Something I also wanted to share today was specific measurements for low latency systems, especially the one that are event-driven. And so here the idea is, so this is going to be, of course it's a very simplified code, it's just an idea. This is how your trading system looks like. There is a while loop, so this is your main event loop. And you polled your network card, you're waiting for some event. And every packet goes into this is interesting function. You can imagine this is kind of your strategy. And then, if it's interesting, you send an order. Now, the tricky part when you measure performance is that, with all the tools that I mentioned in this last hour, is that they're going to have a very hard time to give you a good idea of what's going on in these functions. For the reason that, we looked at perfstat. Perfstat is a very coarse, measurement that are just counters being incremented. So these functions calls are going to be, in the middle of, like putting network cards on, most of the time actually not doing much. Perf record is a sampling profiler. It's just going to sample. You can actually set the sampling frequency. Let's say 1,000 times a second. Most of the time, you're not going to get into these functions. Or if you get into them, you're lucky, but it's not going to be very accurate because you don't really capture the entire function. So what you gotta do here, and I don't think there are actually plenty of different solutions to this problem, if you wanna be as accurate as possible and very low overhead, you do something like this. So you do what we call, intrusive profiling. You modify your code. You have this little object here. You save some metadata. And in the constructor, you start reading the TSC. Okay, now this is again quite x86 specific. Start reading your TSC in the constructor. In the destructor, you read the TSC again, and you have your time interval. And then you can imagine, that you, again, write to a queue. That's why we're looking at queue, because they're a little bit everywhere. Now that's great, but I don't think it's really new. And the main problem of this approach is that you're not going to add this little object that we just looked at everywhere in your code, because then it's not great. You have that just laying around. It's hard to maintain. It has a cost. I mentioned it is low overhead. It's low overhead if you just have this 2 TSC, but if you start having this into every single of your function, at some point you're going to use half of your CPU time just in TSC instructions. So you don't want that. And the challenge here, as an engineer, is that you do not know where the next bottleneck is going to be. And so at some point you have a bottleneck, you need to kind of go back into your code, add this kind of instructions again, recompile your binary, ship it to production, or run some simulation, and so on and so forth. And so this is actually not a great workflow. And so the nice thing here is actually to use X-ray from Clang. And so what's Clang X-ray? Is, you're going to compile your binary with a special flag. I think it's called X-ray instrument. And so this is like an instrumentation library provided by Clang. And so that's awesome. How it works in under the hood is that it's going to add knobs at the beginning and at the end of your function. And so by default, it's not doing anything. You just execute a few knobs at the beginning of your function at the end. So it's very low overhead. But when you want to actually profile, you can patch your binary, and you can replace these knobs with some function calls. So you can have a really nice profiler that is as accurate as you can, low overhead, and at the same time, you avoid recompiling your binary and going through that workflow that I described. And so that's awesome, because it really kind of like gives you like the best of both worlds, where you can really have like a nice workflow as an engineer, measure things, could be in production or not, without having to constantly recompile your code. And then on a similar topic is that, once you fixed, all your latency bottlenecks, etc., you've got a graph like this. I'm actually not saying, what kind of latency this is. It actually doesn't matter too much. But the idea here is once you actually have, a latency that you're happy with, you still have a lot of work to do. Usually that work is a little bit less fun, but it's really important. You gotta measure a lot on your system. And I often say that it's really nice to actually send to a database millions of numbers per second. So all your measurements, that's nice. But what's really important, what actually really matters, is to have alerts, is to have actually the audits on these numbers, right? We can always pump a lot of numbers to the database and look at them with nice graph. If you don't have actual audits on expectation, like things checking these numbers, it is not going to be very useful. Because it's always the same. When you roll out something new, there are all the eyes on it, and then a year later, no one is really looking at it. So you got to have this checks here. And so that brings us to our principle 8. It's nice to be fast. What's really hard here, like what takes a lot of engineering time, is actually to stay fast. We're slowly approaching the end of this talk, and so as an outro, I have one last idea that I find really important, something that kind of like kept coming back, throughout my careers when I would look at latency of this system, and I call it "You're not alone." So in that picture, you see an engineer, a lot of screens, lots of code. It's really easy to forget, that, you're just not here on your own developing code. So let me explain a little bit what I mean with some last snippet of code. So this is a relatively simple code. So what are we doing here? We are generating a vector of shuffle indices. And so we generate a vector. We actually want to run this benchmark for different size, so we care about the working set size. And then once we've got that vector, we are going to sum it in what I would call the worst possible way. Which is you follow all this, you sum it following actually the order of these indices. This is kind of gonna simulate an almost perfect, random walk into memory. And then you measure the throughput. And so the result that you're gonna get is something like this. So let me explain, because there are a few things going on that graph. The blue line, called single worker, is going to be a single instance of this application on a single CPU, with nothing else running on that server. And so what you see when you measure, the throughput, is that you clearly see our 3 level of cache. You see, we start, we are really, high throughput, and then we pass our first level of cache, 32 kilobytes on that server, drop L2, and then we reach L3, drop again, and then we are in RAM. And then you've got 6 workers. The 6 workers, each of them are their own CPU. And so you instantiate 6 instances of this application, and you measure the throughput again. And you see that it's almost the same as the single worker, except around our L3 cache. Effectively, for the integrality of the L3 cache, right? So on this server, it's between, it's around where we start there, like a little bit around 6 megabytes, 8 megabytes. And then up until like 664, on this area of the L3 cache, the performance, this is the scaling factor, if we take the sum of the 6 workers and we divide it by the single worker, we've got our scaling factor, right? How much speed up do we get from having 6 CPUs against 1? And we're not sharing any data really in this code. What we see here is we'd almost go to 1. And we almost go to 1 for our integrality of our L3 cache. And so why is this really, why does this matter? Why, what the point that I'm trying to make here is that effectively, for the vast majority of the system that I've been working on, and I think most trading systems they're not going to fit into your L1 cache. If you're trading very few instruments, and depending on your strategy, you might be able to fit some things into the L2. But most of the time, from experience, you're in this area. You're effectively in this area. In your L3, I mean. And the point here is that you need to think about the system as a whole. That's what I mean with you're not alone. You really need to not just think about your application or, an application A and B, etc. You really need to look at the entire server. And, if this entire server with all the applications that are on it makes sense. Otherwise, there will be no way to actually have something performant and low latency. So the point here is that, today we looked at a lot of examples, optimization, data structure, etc. You can do all that, and still your system will be relatively slow. If not everything on that same server, if not all your colleagues did the same. And so this is our last principle here, which is, I'd say, lesson of empathy, which is you shouldn't just care about the performance of your code. Yeah. It all depends also on the performance of the code of the CPU, things that are running on the same servers. Final thoughts. So we started, looking at, I was saying at the beginning of this talk, market making, loser's game, you need to be consistently good at everything. There is no silver bullet. Well, it's pretty much the same when it comes to low latency programming. There is no silver bullet. We would all love that there is one, but there is none. So you need to be disciplined, keep things simple, because as we thought, simple things are fast. They're not just fast, they're also simple to understand, well, for you, for your colleagues. If they're simpler to understand, you can actually build a simpler system that which, on its own is going to be, again, faster. That's our last point that we looked at. And I probably today, mentioned many times the word latency. There is actually one latency that I didn't mention, which I also wanted to say that it matters, that it's important, which is time to market, effectively. If I actually also today put an emphasis on simplicity, it's also because it does matter really, how fast actually can you ship your code to production. So that's a latency as well. Now going through some credits, just want to say thanks to some colleagues, some people that, helped me build that talk, some people that inspired me, some people that I can bounce idea off. So thanks to them. And then I always like to give references, to go further. There are plenty of interesting things out there. And this is just very much one slide of what, things that I found interesting. There are, some talks there that I really appreciated. And from Fedor, from Mike Acton, some of them are actually quite old, but still extremely relevant for today. So that concludes our talks, and we still have, solid 10 minutes for questions. Yeah, thank you.
Thank you for the talk. So about the sequential search and binary search that you had, did you try like partitioning the thing and doing sequential search for the first few and then doing binary search for the next?
Say that again. So on the binary search, did I try to batch things?
Yeah, like first few you could do like linear search.
Yeah.
And then if you can't find, then you can switch to binary.
Yeah, I actually did try that. Yeah. In general, like I did try a lot of things there. I did try some meta parameters, indeed going between, I think actually Andre presented that in one of his talks. So like, kind of meta parameter between, I think it was about sorting more than searching. I tried that. Effectively, and it might just be like, a property of like the things that we're looking at.
Yeah.
Exactly. Like, I think the idea is just that the collections are not big enough.
Okay.
So in general, linear search is going to just be the best there no matter what. I mean, maybe there is an instrument or something out there with like, I don't know, 100,000 levels, and where indeed linear search would then be slower. Couldn't find it.
Okay, thank you.
Thank you.
Hi, David. Thanks for the talk and for building the toy example of the books for the talk. So pretty much following on the previous question. Well, naturally, like the book updates are heavily skewed towards the top of the book, right? So did you, out of curiosity, try two ideas? So one idea is to split the prices with the rest of the data to compress your vector.
Yep.
And the second one, if SIMD instructions for the like first few levels.
Your second point was AVX or?
AVX.
Ah,
yes.
yeah.
Well, AVX 5512 to slow your frequency, but
So I did try that. Effectively, they go together, because in the code example actually, like we have pairs of elements. We have pairs of price and volume, and effectively the compiler. I mean, maybe one day it will be able to do it, but at least in the state of things, the compiler is not going to generate any AVX instruction with that. And so your first question was, did I try to split vectors? Yes, I did. It had a slight positive effect. But the nice effect about splitting the vectors into two and just having your price and your volume is that once you do your linear search, I mean, very much the find if on your vector, now actually you get the AVX generation for free from the compiler. Because you have all your prices, you just have a vector of U in 64, and then the compiler is actually going to generate AVX. The interesting thing is, so you actually do get, the answer is yes, you have like a slight performance gain of it. I'm not sure if it's true for, like for every single case. That's also why I actually didn't like mention it. But you do get some performance out of it. Because yes, indeed, it's more packed, and AVX effectively results are a little bit mixed. Which is if you have effectively just a few levels, something quite thin, the initial cost of latency of your AVX instruction are going to make it slower. So, yeah, it's a little bit mixed.
I see.
Yeah.
Thank you.
Thank you.
Hey, hi. That was a great talk. The fast queue which you explained was an in-memory queue. So have you ever encountered a case where you want to store the state of the events which are going through the queue?
The state of the events that are going through the queue?
Yeah, let's say if my process crashes and I want to build the state of the messages which were passing through that queue.
Yeah.
So
yes.
How does it impact your, like, first thing, how do you do it? And how does it impact the latency?
You should look at, for example, Postgres internals. Might be familiar with like how database work. They use like a so-called WAL, so WAL. you can look at this data structure and this is what you want.
So you basically store it in the database. That's what you're saying?
No, sorry. No, I didn't mean to use the database. I meant to look at the data structure used in a database like Postgres. There is this thing called WAL, W-A-L, which is what you want. So I don't mean to use the database, but just this data structure can actually do what you want here, which is in case there is actually a writer or, that crash, you actually persist on disk and you avoid any loss of data. I mean, the queue that I presented here clearly doesn't do it, but it is an element, a building block of such structure.
So essentially, if my multiple processes are on the same machine and I implement write-ahead lock, which you talked about right now, along with the fast queue implementation, that might give me a better performance than RabbitMQ, which is across the different networks.
Sorry, can you say that again? Actually, I'm not sure if I follow. You mentioned a few different things here, multiple producers.
Yeah, so what I'm saying is, if we are able to implement the WAL, the write-ahead lock, along with the fast queue implementation, which you explained, right? I think fast queue implementation doesn't have the WAL implemented in it, right?
No, absolutely not.
Okay, so that can it be a better solution than using RabbitMQs, like technologies, right?
Whoa,
RabbitMQs?
I do not know. But this is too specific. I know RabbitMQ, never used it. My gut feeling is yes, but I don't want to say yes too quickly. So, I mean, you gotta just look at it, cool. Measure.
Thanks for that.
Yeah, for sure. Thank you.
Hi. Thanks for the talk. I think I have a question about the security. So in your implementation, you mentioned we can use share memory, and we can also avoid to copy data to improve the performance. Yeah. But in previous talk, I heard something like TOC, TOU, time to check, time to use. That is, attacker may use, if we use share memory, attacker may change the input data after we validate it. So how do you think if we use shared memory, how we can prevent this kind of attack?
So what kind of attack exactly is this?
The name is TOC, TOU, time to check, time to use.
Right.
Yeah.
And can you be like, so what
basically it's a kind of attack that after our program validate the input is legit. And after that, because we use shared memory,
yeah.
So attacker can change our input.
You're talking about very much like an attacker, like you mean like, you're talking about like vulnerabilities, security, etc., right? You mean like someone that would exploit?
Yeah.
Wow, that's great question. I actually have to pass on this one. I don't have much opinion there, mostly because, I mean, I guess I do, but I'm definitely not an expert there. Yeah, I really can't say much. The thing with like the area of like, trading system is that our processors are always on servers that we own, that are in, part of our servers or our racks. So effectively, yeah, here, this is actually not, I mean, definitely security is a thing, right, on a company level. But when it comes to like such data structure on the shared memory, I'm actually not too worried about attackers, like looking at my RAM. So, yeah, I gotta pass on this one.
Okay.
Hello, I'm also from another trading firm, so like it's very interesting talk about like low latency in trading system. So I want to ask one question regarding like the use of so-called struct of arrays. Like you demonstrated like this linear search. I believe like using struct of arrays should reduce the number of like catch misses, things like that. I'm wondering, like, does Optiva use struct of arrays like technology internally? And if you do you have some kind of like framework to make it easier?
Yeah, absolutely. Effectively, that's why I put as a reference Mike Acton here. So that this talk is about like, what you just mentioned. And effectively, the previous question was also a little bit about that. So we're definitely using it. Now, we use it where it's needed. So what I mean is that it's not like something that like we follow on everything in the struct of array. But like very much, yes, in some cases, it does help. And so as I said actually in a previous answer, for the very specific case of this vector with like these pairs, yeah, you can split it. And you do get actually like some performance gain out of it.
So you mean like it's mostly kind of manual, like you only if it's needed, you do some manual like refactoring to make it structure free, but there's no fun work.
No, we're usually quite pragmatic about these things, and like we definitely use something when it's strictly needed, and maybe it's a bit of a, like at least I tend to, I probably say that word too many times today, like I have strong opinions about like simplicity. I like to keep things very simple. I'm also like very like wary about pulling dependencies. So frameworks to do something like struct on array. Yeah, struct on array is a simple thing. So, I can do it. I can just do it on my own, reason about it. I'm like sometimes wary about pulling an entire framework to do this. Sometimes this abstraction layer, I'm not saying that not needed. Sometimes they're great, but sometimes it's also like, except if it's literally everywhere in your code base, but that's actually also not our case.
Thanks.
Yeah, thank you.
Hello, thank you for the talk. I was going to ask about the Linux message queues. We have a real-time application, probably not quite as demanding as yours. There's not as much money on the line, but we have multiple processes that need to communicate, and we're using the Linux message queues. We're using SUSE Linux, similar to the Red Hat Linux that you're using. And I wonder if you could give me a feel for how the underlying message queue implementation in the Linux kernel differs from the custom message queue that you're using, or did you look at that?
It's a great question. I actually didn't really look at like the implementation of what like of the queues that you're referring. Which one are you referring? I believe that there are multiples. Do you have a specific name?
I'm not that familiar with the underlying technology because we have a wrapper that we call system services.
Right.
I believe it's calling down to the Linux messaging function. I believe there's a level function there.
In general, the Linux kernel, I would think that like the queue implementation, right? that they use there is not really the problem. It's probably going to be very fast. I can totally trust that. The main problem with going to the kernel are going to be syscalls, and so the variants that you get from syscalls. So that's a little bit the same as like network, user spacing or not, which is like as soon as you go into the kernel, the variance and the jitter that you have from like going from user land to kernel land, that is actually the main thing that we want to prevent here. But I really, I can trust the Linux kernel developers that probably have very fast data structure in there.
Thanks, that's a great answer. I appreciate it.
Thank you. But I think we're out of time. I will still, stick around for more questions. But yeah, thank you all. Thank you.